So, this is a stochastic processes module 1 probability theory refresher, lecture 4 problems in sequence of random variables. As a illustrative examples, we are going to discuss 4 problems in this lecture. The first problem, let Z1, Z2, so on be a sequence of random variables, each having Poisson distribution with parameter n, that is Zn is Poisson distribution with the parameter n for n is equal to 1, 2, 3 and so on. Our interest is to find the limiting distribution of the random variable that is defined as y suffix n, that is Zn minus n divided by square root of n. So, given Zn is Poisson distribution with the parameter n, we can find out the MGF of Zn. MGF of Zn is nothing but expectation of e power Zn of t, that is same as summation k is equal to 0 to infinity e power k times t e power minus n power k by k factorial, because it is a expectation of e power Zn of t, where Zn is Poisson distribution with the parameter lambda. Therefore, this is going to be n k is equal to 0 to infinity this form. So, you can take e power minus n outside. So, the remaining term becomes k is equal to 0 to infinity e power t multiplied by n, the whole thing power k by k factorial. That is same as e power minus n e power n times e power t, that can be rewritten as e power n times e power t minus 1. Now, we will find out the MGF of the random variable yn, where yn is Zn minus n divided by square root of n. Therefore, the MGF of the random variable yn as a function of t, that becomes MGF of Zn minus n divided by square root of n function of t, that is same as expectation of e power Zn minus n divided by root n multiplied by t. You know the rules of a moment generating function, the constant is out. So, you can use that logic. So, it becomes e power minus t times root n, because n t by root n, therefore, it becomes a t times root n. Then MGF of the random variable Zn, use the another rule of a moment generating function, instead of t it becomes a t divided by square root of n. So, that is same as e power minus t times root n. Just now we found what is the moment generating function of Zn. So, use the same thing, but replace t by t divided by square root of n. Therefore, this becomes e power n times, wherever the t you replace t by square root of n. So, t by square root of n minus 1. Therefore, you can further simplify by expanding e power t by n. That means, you keep this e power n, you expand only e power t by square root of n, that is 1 plus t divided by square root of n, then the next term will be t square by 2 times n, and the next term will be t cube divided by 3 factorial n power 3 by 2 and so on, and the last term is so this is the expansion of e power t by square root of n minus 1. So, close the bracket, that is same as e power t times square root of n multiplied by, so this 1 and plus 1 and minus 1 will be cancelled. So, you will get e power n times t by square root of n, that becomes t of square root of n, and the next term becomes t square by 2, then it becomes t cube by 3 factorial n power 1 by 2 and so on. Therefore, this becomes e power t square by 2 plus t cube by 3 factorial square root of n and so on. Our interest is to find out the limiting distribution of y n. So, this is the moment generating function of y n for n. So, as n tends to infinity, because our interest is to find out the limiting distribution, as n tends to infinity, the moment generating function of y n becomes e power t square by 2. If you recall, the moment generating function for standard distributions, one can conclude this is the MGF of a standard normal distribution. Therefore, we conclude the limiting distribution of y n is a standard normal distribution. That is the limiting distribution z n minus n divided by square root of n is a standard normal distribution. So, this problem is very important in the renewal processes. Therefore, we discuss this example as how to find the limiting distribution of some standard random variables. Next example, let x1, x2 and so on be a sequence of random variables, each having CDF cumulative distribution function f suffix x n of x, it is 0 from minus infinity to 0, and it takes a value 1 minus x by n power n for x is lies between 0 to n. From n onwards till infinity the value is 1. So, this is the cumulative distribution function for the random variables xi's. It is a function of n, therefore, I have made it f suffix x suffix n. That means, this is a CDF for the random variable n. For every n you have this form. As n tends to infinity, we get f suffix x n of x that becomes 0 from minus infinity to 0, and it takes a value 1 minus e power minus x from 0 to infinity. As n tends to infinity, the CDF of the random variables x n becomes 0 between the interval minus infinity to 0, and the value becomes 1 minus e power minus lambda x, where x is lies between 0 to infinity. Suppose x is a random variable with the CDF that is f x of x, that is 0 between the interval minus infinity to 0 and 1 minus e power minus lambda x, where x is lies between 0 to infinity, then one can conclude x n converges to x in distribution, since the sequence of f x suffix n of x tends to f of x for x is greater than or equal to 0 and the value is 1 minus e power minus x. Hence, one can conclude the sequence of random variable x n converges to the random variable x in distribution. Here the x is a exponential distribution with the parameter 1. So, this is the one example of how the sequence of random variable converges to a random variable in distribution. Next, I will move into the third example. Suppose we choose at random n numbers from the interval zero to 1 with the uniform distribution let capital Xi be a random variable describing the ith choice. Then for I is equal to 1, 2 and so on, you can find out what is the expectation of Xi's, that is nothing but the integration from 0 to 1 x times the probability density function. The probability density function for uniform distribution with the interval 0 to 1, that is 1. Therefore, x into dx, if you compute, the expectation of Xi is going to be 1 by 2. Similarly, one can evaluate the variance of Xi's, that is nothing but 0 to 1 x square dx minus the mean square, expectation of x square minus expectation of x whole square. So, the expectation of x square is 0 to 1 x square dx. So, if you evaluate this quantity, that is 1 by 3 minus 1 by 4. So, if you simplify, you will get 1 by 12. If you remember the formula of variance of a uniformly distributed random variable between the interval a to b, then the variance of x is nothing but you can get it by substituting the value of a is equal to 0 and b is equal to 1, you will get 1 by 12. Let s suffix n be x1 plus x2 and so on till xn. One can find mean and variance of Sn, because you know the mean and variance of Xi's. Using that, you can find out what is the mean of Sn, but our interest is not the finding the mean of Sn, our interest is to find out the mean of Sn by n. That is basically, suppose Xi's are the samples, then Sn divided by n is nothing but the sample mean. So, expectation of Sn divided by n, that becomes 1 by 2. Similarly, if you calculate variance of Sn by n, that becomes 1 divided by 12 times n, because the variance of Xi's is 1 by 12. So, the variance of Sn is a summation of Xi's from 1 to n. Therefore, variance of Sn by n becomes 1 divided by 12 times n. For any epsilon greater than 0, using Chebyshev inequality, one can conclude the probability of absolute of Sn by n minus 1 by 2 greater than or equal to epsilon, that is less than or equal to 1 divided by 12 times n epsilon square. I am using the Chebyshev inequality by knowing mean of Sn by n is 1 by 2 and variance of Sn by n is 1 divided by 12 n, I get this inequality. Now, as n tends to infinity, the probability of absolute of Sn by n minus 1 by 2, which is greater than or equal to epsilon, will tends to 0, because epsilon is in the n is in the denominator, because n is in the denominator. As n tends to infinity, this probability tends to 0. That is nothing but Sn by n tends to the value 1 by 2, and this convergence takes place in probability. The sequence of random variable Sn by n converges to 1 by 2 in probability. Therefore, we say the sequence of random variable x n for n is equal to 1, 2 and so on obeys the weak law of large numbers, because the S n by n converges to 1 by 2 in probability. Therefore, we say the sequence of random variables say x n's obeys the weak law of large numbers. So, that is the intention of giving this example. Now, I move into the fourth example. Consider a repairman who replaces a light bulb the instant it burns out. Suppose the first light bulb is put in at time 0 and let x suffix I be the lifetime of ith light bulb you define the random variable T n is the sum of n x's where x's are IID random variables. Xi be the lifetime of the ith light bulb, and when x's are IID random variable, you are defining Tn is x1 plus x2 plus xn and so. So, the Tn be the time the nth light bulb burns out, because the Tn is x1 plus x2 and so on till xn. Therefore, Tn be the time the nth light bulb burns out. Assume that x size is exponential distribution with the parameter lambda. We know that already x i's are IID random variable. Now, I am making the further assumption x size follows exponential distribution with the parameter lambda. That means, you know what is the mean of this random variable. Since it is exponential distribution with the parameter lambda, this becomes 1 divided by lambda. Also, one can use the result Tn by n, that is nothing but 1 divided by n summation of x i's, where I is running from 1 to n, as n tends to infinity, one can prove Tn by n tends to 1 divided by lambda, that is a mean of the random variable xi almost surely. I am not proving here. The way you do the sequence of random variable converges to another random variable, convergence takes place in probability or in distribution or in orth mean or almost surely. One can prove this, that Tn by n converges to 1 by lambda almost surely. That means we can conclude the random variable x1, x2 and so on obeys strong law of large numbers, because the Tn by n, that is nothing but 1 by n of summation of xi's, that converges to the value 1 by lambda almost surely. We can conclude the sequence of random variable xi's obeys a strong law of large numbers. Even though in this problem I made the assumption xi's follows the exponential distribution with the parameter lambda, in general the lifetime can be any distribution. So, this problem will be discussed in detail in renewal processes. So, as such here we are making the assumption of a distribution of xi's is exponential distribution, therefore, I made it convergence takes place almost surely to the value 1 by lambda. This can be generalized. There are many more problems of the similar kind, but we are discussing only few problems. Therefore, we can use a similar logic of finding the moment generating function, then concluding the distribution and finding the limiting distribution, or you verify whether the sequence of random variable convergence takes place in mean, convergence takes place in probability, or convergence takes place in distribution, or convergence in the orth mean, or convergence almost surely. This can be used in any problem of the same way what I have done it here. And I have not discussed any problem in the central limit theorem, but that will be used many times. Therefore, I have not given any problems for the central limit theorem. So, these are all the reference books. We have used it for the lecture 3 as well as lecture 4. Kitna time? So, what to do? Then we may go to some more problems then. मेरा लैपटॉप ओपन कीजिए, we'll cook up one problem. I didn't realize that I may land up. Let x1, x2, so on be a sequence of random variables each having student t distribution with the n degrees of freedom. Our interest is to find out the limiting distribution of the student t distribution. We know that the probability density function of f of x for the random variable x n is given by gamma of n plus 1 by 2 divided by square root of n times pi multiplied by gamma of n by 2 multiplied by 1 plus x square by n the power minus n plus 1 by 2. So, this is the probability density function of a random variable x n. Our interest is to find out the limiting distribution of the random variable x n. For large n, we have the results limit n tends to infinity of gamma of n plus 1 by 2 divided by square root of n pi of gamma of n by 2 is 1 divided by square root of 2 pi using Stirling's approximation. And also limit n tends to infinity of 1 plus x square by 2 the whole power minus n plus 1 by 2 that we know that is e power minus x square by 2. Hence, the limit n tends to infinity of the probability density function of the random variable x n becomes 1 divided by square root of 2 pi e power minus x square by 2. Since the right hand side is the probability density function of a standard normal distribution, we conclude for a larger n the sequence of random variables x 1, x 2, x n and so on that tends to the random variable z, and this convergence takes place in distribution where z is standard normal distribution. So, this is a simple example of the sequence of random variables each having a student distribution. The limiting distribution converges to standard normal and that convergence in distribution. Now, moving to next example. Example 6. Let x 1, x 2, so on be a sequence of independent random variables each having probability mass function probability of x i is equal to 1, that is same as probability of x I takes a value minus 1, the probability is 1 by 2. This is valid for that means it is a sequence of IID random variables and they are discrete type. Define m suffix k as the sum of first k xi random variables. So, this running index is k is equal to 1, 2 and so on. So, we are defining a sequence of a random variable m k by summing first k xi random variables. For a fixed integer n, we define another sequence of random variable that is denoted by w superscript n of t, that is nothing but 1 divided by square root of n m suffix n times t. This is for all t greater than or equal to 0, such that n times t is an integer. So, we are defining another sequence of random variables w superscript n of t, that is 1 divided by square root of n times m n of t, where n of t is an integer. So, this is valid for all t greater than or equal to 0. If you find out the mean and variance for the difference of the random variable of n of t minus w n of s for 0 less than or equal to s less than or equal to t, this quantity will be 0. That means w n of t is 1 divided by square root of n m n of t, and the way we define the m n of t, that is a summation of xi's, and the probability of xi is equal to 1 and the probability of x is equal to minus 1 is 1 by 2. Therefore, the mean of xi's are going to be 0. Because of that, the expectation of or mean of w n of t minus w n of s, that is equal to 0. Also, if you evaluate the variance of w n of t minus w n of s by finding first variance of xi's, using that you find out the variance of m n of t, then find out the variance of w n of t minus w n of s, that is going to be t minus s. It need a calculation of expectation of xi square, then using expectation of xi square and the expectation of xi's, you can find out the variance of xi's. Using variance of xi's, you can find out the variance of w n of t, then you find out the variance of w n of t minus w n of s. By using mean and variance for fixing t greater than or equal to 0 as n tends to infinity, we can conclude w n of t tends to a random variable x, and this convergence takes place in distribution. Using CLT, one can conclude w n of t converges to the random variable x and the convergence in distribution, where x is normal distribution with the mean 0 and the variance t. Using a central limit theorem, one can prove w n of t converges to x in distribution, where x is a normal distribution with the mean 0 and the variance t. This result is very useful in Brownian motion, and this same problem will be discussed in detail when we are discussing the model of Brownian motion.